Now we are going to start the third chapter, metals and nonmetals. Metals are those elements which can lose electron easily and form positive ions, whereas nonmetals are those elements which can gain electron and form negative ions. Now we are going to take up properties of alkali metals. Sodium and potassium are highly reactive metals and soft metal. They can be cut with knife. This reaction shows that potassium and sodium catches fire when put in water. Vinegar is acidic in nature and baking soda is basic in nature. They are reacting together and liberating carbon dioxide. And baking soda also neutralizes the hyperacidity in our stomach. This is sodium hydroxide solution which is used for removing grease and used to clean. Calcium and magnesium are harder metals. Calcium still can be cut with knife. Calcium and magnesium react with water. Magnesium reacts with hot water, but calcium reacts with cold water vigorously and hydrogen gas is formed. This is calcium hydroxide which is used for neutralizing acidity of the soil. Calcium and magnesium ions form hard water. And barium hydroxide is used in X-ray tubes to get X-rays of intestinal tract. This table shows how to identify a metal and non-metal. First identification can be done with the help of valence electrons. Valence electrons are electrons present in outermost shell of an element. Generally, metals have 1 to 3 valence electrons. Tin and lead are exceptions. They have 4 valence electrons, but still they are metals. Non-metals have 4 to 8 valence electrons generally, but there are exceptions. Hydrogen and helium have 1 and 2 electrons respectively, but still they are non-metals. Second way of identifying metals and non-metal is by measuring the tendency to lose or gain electrons. Metals have tendency to lose electron and form positive ion. That is, they are electropositive in nature, whereas non-metals have tendency to gain electron and form negative ions. That is, they are electronegative in nature. So, ion formation, metals will always form positive ions. Positive ions are also called cations because they are attracted towards cathode. Non-metals form negative ions which are also called anions because they are attracted towards anode. Now, metals are good reducing agent. Why they are good reducing agent? Because they can lose electron easily. Non-metals are good oxidizing agents because they can gain electron easily. This is reactivity series of metal. Reactivity series is the series of metals in which the most reactive metal is at the top and least reactive metal is at the bottom. The most reactive metal in reactivity series is potassium. Potassium is followed by sodium, calcium, magnesium, aluminium, zinc, iron, lead. Now, hydrogen is not a metal, but still it is included in electrochemical series or reactivity series of metals because it can form positive ions. Copper, mercury, silver and gold are metals which are less reactive than hydrogen, therefore they are below hydrogen. And all the metals which are above hydrogen are more reactive than hydrogen. All the metals which are more reactive than hydrogen can displace hydrogen from water and dilute acids, whereas those metals which are less reactive than hydrogen cannot displace hydrogen from dilute acids and water. That is, reactivity goes on decreasing in this reactivity series of metals. Now we are going to take up reaction of metals and non-metals in air. Sodium is highly reactive metals and it reacts with oxygen present in air and result in the formation of sodium oxide. This equation is not balanced. This side we have got 2 oxygen, so it is to be multiplied by 2. Now we have 4 sodium, so it will be multiplied by 4. Now the equation is balanced. Potassium reacts in the same manner. 4 moles of potassium reacts with oxygen gas and it results in the formation of potassium oxides, which is solid. Now we want to test that sodium oxide is a acidic, basic or neutral. We will dissolve it in water. It results in the formation of sodium hydroxide, which turns red litmus blue. It shows that sodium oxide is basic in nature. Similarly, potassium oxide, when dissolved in water, it will form potassium hydroxide. Potassium hydroxide is also basic in nature. When non-metals react with oxygen, they form acidic oxides. For example, sulfur burns in presence of oxygen and result in the formation of sulfur dioxide. Carbon reacts with oxygen on burning and result in the formation of carbon dioxide. How do we find out these oxides are acidic, basic or neutral? Sulfur dioxide, when dissolved in water, it results in the formation of sulfurous acid, which turns blue litmus red. Similarly, carbon dioxide, when dissolved in water, it results in the formation of carbonic acid, which also turns blue litmus red. This shows that metals form basic oxides and non-metals form acidic oxides. Aluminium reacts with oxygen to form aluminium oxide. The formula is Al2O3. This equation needs to be balanced. We will multiply it by 2. 4 aluminium plus 3 O2 gives you Al2O3. Aluminium oxide is acidic as well as basic. Therefore, it is amphoteric in nature. In the next reactions, we will show you how aluminium oxide is amphoteric in nature. Let's take up how aluminium oxide is amphoteric in nature. I have told you that it is acidic as well as basic. If it is basic, it should react with acid. Aluminium oxide reacts with acid to form aluminium chloride plus water is formed. To balance this reaction, we will put 2AlCl3. So here chlorine has become 6. So we multiply HCl by 6. Now to balance it, 3 water we will add. Now this equation is balanced. This reaction shows that aluminium oxide is basic in nature. Now if aluminium oxide is acidic in nature, it should react with base. Aluminium oxide reacts with base to form sodium meta-aluminate and water is formed. To balance it, we multiply it by 2 and here also multiply it by 2 and this equation is balanced. Now we have shown that aluminium oxide forms a salt and water with acid as well as base. It means it behaves like acidic as well as basic. That is, it is amphoteric in nature. Now we are going to take up reaction of metals with dilute acids. Let's take up reaction of iron with dilute HCl. When reaction of iron and dilute HCl takes place, we get FeCl2 plus hydrogen gas is formed. Now Fe will react with 2HCl, dilute acid, and it will result in the formation of FeCl2 aqueous plus hydrogen gas is formed. In the same manner, magnesium reacts with dilute hydrochloric acid and result in the formation of MgCl2 aqueous plus hydrogen gas is formed. Aluminium also reacts with dilute HCl and this time we are going to get aluminium chloride. Valency of aluminium is 3, that is why AlCl3 is formed plus hydrogen gas is formed. To balance, 2 aluminium reacts with 6 HCl to form 2 AlCl3 and 3 hydrogen are formed. Now if we react dilute nitric acid with metal, then generally hydrogen gas is not liberated. Reason is that dilute nitric acid is a oxidizing agent. That is why we get nitrogen monoxide, and with concentrated nitric acid we get nitrogen dioxide. But there are two metals, magnesium and manganese. they react with very dilute nitric acid, that is just 5%. 5% means you will take 5 ml of concentrated nitric acid and remaining 95 ml of water you will add. They will liberate hydrogen gas. So this is the only exception, and this takes place only in case of very dilute nitric acid, and only two metals react in this manner, that is manganese and magnesium. Both will form their respective nitrates plus hydrogen gas will be evolved. This table shows reaction of metals with cold water, hot water and steam, and what do we observe and what is the chemical reaction taking place. The first metal we are going to take up is zinc. Zinc can react with steam as well as hot water, and when it reacts it forms zinc oxide, which is white powder, and side by side hydrogen gas will be formed. The reaction, if you see, zinc metal reacts with steam or hot water to form zinc oxide, which is white solid, and hydrogen gas is evolved. Aluminium reacts only with steam. It does not react with hot water as well as cold water, but reacts only with steam. Aluminium reacts with steam to form aluminium oxide, which is also white solid, and hydrogen gas is formed. The reaction will be 2 aluminium plus 3 water gives you Al2O3 solid plus 3 hydrogen is formed, and this equation is balanced. Copper does not react with cold water, hot water as well as steam. The reason is that copper is less reactive than hydrogen. It cannot displace hydrogen from water. Iron reacts only with steam and it forms Fe3O4 and hydrogen. Fe3O4 is a double oxide. It consists of iron 2 oxide and iron 3 oxide. The chemical reaction taking place is 3Fe plus 4 water in the form of steam reacts to form Fe3O4 solid, and 4 moles of hydrogen gas are formed. Magnesium reacts with hot water, and because it is lighter it floats over water. Magnesium hydroxide is formed and hydrogen gas is formed. Magnesium is reacting with 2 moles of water and we are getting magnesium hydroxide and hydrogen gas. We observe bubbles due to hydrogen gas in these reactions. Now we are going to take up reaction of highly reactive metals like sodium, calcium, potassium with cold water. When we react sodium with cold water, it catches fire. Why it catches fire? Because this reaction is highly exothermic and hydrogen gas which is evolved catches fire. The chemical reaction taking place is sodium reacts with water to form sodium hydroxide and hydrogen gas. For balancing, it will be 2 sodium plus 2 water gives you 2 moles of sodium hydroxide and hydrogen gas is formed. Calcium reacts with cold water, vigorous reaction takes place, and calcium floats over water because it is lighter, and the product formed are calcium hydroxide and hydrogen gas. The chemical equation taking place is calcium plus 2 water gives you calcium hydroxide plus hydrogen gas is formed. Potassium is highly reactive metal out of all these, that also catches fire when it reacts with cold water. The chemical reaction taking place is 2K plus 2 water gives you 2 KOH plus hydrogen gas is evolved. Mercury does not react with cold water or hot water or steam, reason being that it is least reactive and it cannot displace hydrogen from water. Now we are going to take up electronic configuration of some of the elements. First we are taking noble gases. First noble gas is helium. Helium has atomic number 2, that is it has 2 electrons and 2 protons. If we take electronic configuration, the first shell, that is K shell, will have 2 electrons. It is highly stable because its first shell is full. Neon has atomic number 10. Its electronic configuration is 2,8. It is also stable because its second shell is full, that is its octet is complete. Argon is the third noble gas whose atomic number is 18. its electronic configuration is 288. This is also least reactive or stable because its valence shell has 8 electrons, that is, its octet is complete. These noble gases are least reactive because they have stable electronic configuration. First metal we have sodium. It has got atomic number 11. Its electronic configuration is 281. Its valence electrons are 1 and it can lose 1 electron very easily. That's why we classify it as metal. Magnesium has atomic number 12, that is, it has 12 electrons and distribution of electrons will be 282. It can lose 2 electrons easily, that is why it is regarded as metal. Third metal is aluminium. Aluminium has atomic number 13, that is, it has 13 electrons. The distribution of electron in various shells is 283. It has 3 valence electrons. It can lose 3 valence electrons easily to form aluminium tripositive ion. Potassium is highly reactive metal. Its electronic configuration will be 2881 because its atomic number is 19. Now last shell cannot have 9 electrons because it's a rule that last shell can have only 8 electrons or less. Therefore its electronic configuration is 2881. It has 1 valence electron, so it can lose 1 valence electron easily to form potassium ion and acquire stable configuration of argon. Calcium has atomic number 20, that is, it has 20 electrons. The distribution of electrons will be in the same way, 2882. It has 2 valence electrons and after losing 2 valence electron it forms calcium dipositive ion and acquires the noble gas configuration, which is very stable. Now we are going to take up non-metals. The first non-metals we are taking is nitrogen. Nitrogen has atomic number 7. It has electronic configuration 2 and 5. It has 5 valence electrons and it can gain 3 electrons more to become 8 valence electron like noble gases, that is neon. Oxygen has atomic number 8. Its electronic configuration is 2, 6. It can gain 2 electrons to become stable, that is 8 electrons in its valence shell. The third non-metal is fluorine. Fluorine has atomic number 9. Electronic configuration is 2, 7. It can gain 1 electron to form fluoride ion and acquire the nearest noble gas configuration, that is neon. After fluorine we have phosphorus. Phosphorus has atomic number 15. Electronic configuration is 285. It can gain 3 electrons to become stable to have same configuration as that of argon, which is more stable. After phosphorus we are going to take up sulfur. Its atomic number is 16. Electronic configuration 286. That is, it has 6 valence electrons. It can gain 2 electrons to form S2 negative ion, that is sulphide ion, which is stable like argon. Last non-metals we are taking is chlorine. Chlorine has got atomic number 17. Its electronic configuration is 287. It can gain 1 electron to become stable to form chloride ion and its electronic configuration will be same as that of argon. So every non-metal can gain electron to become stable like noble gas. Now we are going to take up how ionic or electrovalent compounds are formed. Metals can easily lose electron to form positive ions. For example, sodium has electronic configuration 281. It can lose 1 electron and result in the formation of 28, that is sodium ion. 1 electron is lost and it has become stable. Chlorine has got electronic configuration 287. It can gain 1 electron to form chloride ion. Now if we want to show electron dot diagram, we will show Na positive ion in bracket, and because it has lost 1 electron, therefore it has acquired positive charge. Chlorine was having 7 valence electrons before gaining one electron. So this 7 valence electron, and now it has gained one electron, total electron has become 8, and due to 8 electrons it has acquired negatively charged. This is electron dot diagram of sodium chloride, which is an ionic compound. Now we are going to take up formation of magnesium chloride. Magnesium has atomic number 12. Its electronic configuration is 282. It can lose 2 electrons to form magnesium dipositive ions. Magnesium dipositive ions has stable electronic configuration of neon, that is 2,8. Chlorine will gain 1 electrons to form chloride ion. But here magnesium has lost 2 electrons. So 2 chlorine atoms will gain 2 electrons and form 2 chloride ions. Then only the electroneutrality can be maintained. When you want to write magnesium chloride electron dot diagram, first we write magnesium ions in bracket. Then we write chloride ion with 8 electrons with the help of dot, and it has acquired -1 charge. But there are 2 chlorine atoms which have gained 1 electron each, therefore we write twice. This is the electron dot diagram of magnesium chloride. Now we are going to take up melting and boiling points of some ionic compounds. Metals and nonmetals, when they combine, they form ionic compounds. Ionic compounds are those compounds which, when dissolved in water, form ions. The first ionic compound which we are taking is sodium chloride. It has got sodium positive ion and chloride ion. Because they are oppositely charged ions, therefore there is a strong electrostatic force of attraction between sodium ion and chloride ion. That is the reason its melting point is very high, that is 1074 Kelvin. Its boiling point is also high, 1686 Kelvin. Lithium chloride, on the other hand, has slightly lower melting point as compared to sodium chloride. It has got 887 Kelvin melting point and its boiling point is 1600 Kelvin. Calcium chloride is another ionic compound which is made up of calcium ion and chloride ion. Its melting point is 1045 Kelvin and 1900 Kelvin is the boiling point. Calcium oxide is made up of calcium ions and oxide ions. Because they are di-positive and di-negative ions, there is a strong force of attraction and melting point is very high, that is 2850 Kelvin, and boiling point is 3120 Kelvin. Magnesium chloride, on the other hand, is made up of magnesium ions and chloride ions. Its melting point is 980 Kelvin and boiling point is 1685 Kelvin. Now we are going to take up how metals are extracted from their ores. The first step is concentration of ore. Concentration of ore means that removal of impurities from the ore. Ore we take out from the earth, it has sandy, rocky materials which needs to be removed. So by suitable methods like hydraulic washing, froth flotation process, or the other methods we can use for concentration of ores. After we remove the impurities from the ore, we have to take up what type of metals are present in that ore. If metals are of very high reactivity, then we can extract the metal by electrolysis. But electrolysis of highly reactive metal is done in molten state, not in aqueous solution. Reason being that metals will react with water and they will liberate hydrogen gas and hydroxide will be formed. So molten state, that is melted state, if we carry out electrolysis, we will be able to get these highly reactive metals. But these metals now which we will get will be in impure form and they needs to be purified. So by suitable method of purification like electrolytic refining or distillation or liquefaction or oxidative refining, we can convert the given metal into pure metal. Now we have other metals which have medium reactivity. Those metals which have medium reactivity, they may found in the form of either carbonate ore or sulphide ore. If the metals are in the form of carbonate ore, then we have to carry out calcination. Now why do we need to do calcination? Because reduction of carbonate ore directly is difficult, and when we do calcination of carbonate ore, the carbonate ore gets converted into metal oxide plus carbon dioxide is formed. Now metal oxides are very easily reduced with the help of suitable reducing agent. Now when we have sulfide ore, they also need to be converted into oxide with the help of process called roasting. In calcination, we heat carbonate ore in absence of air to get oxide and carbon dioxide, whereas in roasting, sulfide ores are heated in presence of oxygen so as to get oxide of metal and sulfur dioxide is formed. So in both the cases, the final product is oxides of metal, and oxides of metals are easily reduced with the help of suitable reducing agent. And when we reduce oxide of metal, we get metal, that is free metal. Free metal is again in impure form, and impure form metal has to be converted into pure form, and most commonly used method is electrolytic refining. Metals of low reactivity like mercury is also present in the form of sulfide ores, that is HGS. Now their sulfide ores can be roasted directly in the presence of oxygen, and here the oxide which is formed is highly unstable, and that oxide directly changes into metal and sulfur dioxide is formed. And mercury, because it is liquid, it is refined by distillation, and we can get pure mercury after distillation, and distillation method is used for purification of those metals which have low melting and boiling points. Let's take up electrolytic reduction. Highly reactive metals like sodium, potassium, calcium, aluminium cannot be obtained by chemical reduction because they themselves are very good reducing agents. They can be obtained only by electrolytic reduction. For example, if you want to extract sodium metal, you have to take molten NaCl. Now sodium chloride has got very high melting point. It is to be mixed with calcium chloride so as to reduce its melting point as well as increase electrical conductivity. When electric current is passed, we will get sodium metal plus chlorine gas will be formed. This is the net reaction which is taking place. If we write stepwise, then sodium chloride will break down into sodium ion and chloride ion. Sodium ion will be attracted towards cathode. They will gain electron and form sodium solid. Chloride ion will lose electron at anode. This will take place at cathode, whereas chloride ion will lose electron at anode and result in the formation of chlorine atom. Chlorine atom is unstable. It combines with another chlorine atom to form chlorine gas. That is how electrolytic reduction takes place. Electrolytic refining is a process of obtaining pure metal by the process of electrolysis. In this method, an electric current is passed through a solution called electrolyte that contains dissolved metal. This causes the dissolved metal to deposit on the negatively charged cathode. Now we are going to take up refining of copper. In this process, impure metal, that is impure copper, is taken as anode, whereas pure copper is taken as cathode. Acidified copper sulfate solution is taken as electrolyte. When we pass electric current through the electrolyte, you can observe that copper from impure copper anode gets dissolved in the solution as copper plus 2 ions. These ions get reduced, that is gain electron at copper cathode and get deposited on it. On the other hand, the sulfate ion migrate to impure copper anode and combine with it to form copper sulfate, which goes to the electrolyte. Reactions taking place in this process are: at cathode, copper ions gain 2 electrons and form copper solid, that is pure copper. At anode, copper loses 2 electrons to form copper ions. Impurities like silver and gold, which are less reactive, are collected as anode mud. Let's take up extraction of metals. In extraction of metals, it depends upon the reactivity of metals which method we will use for extraction. For example, cinnabar is HGS. When its roasting is done, what is roasting? Heating of ore in presence of oxygen. When cinnabar is roasted, it results in the formation of mercuric oxide solid plus sulfur dioxide gas is formed. To balance it, 2HGS plus 3O2 gives you 2HGO plus 2SO2. This HGO solid is thermally unstable, means on heating it will change to mercury, which is liquid, plus oxygen gas will be formed. So this way we have extracted mercury from cinnabar. If you want to extract zinc, then there are two ores of zinc. One ore is zinc sulphide or zinc blendy. First step will be roasting. Roasting means you will heat in presence of oxygen. It will result in the formation of zinc oxide solid plus sulfur dioxide gas will be formed. To balance it, 2ZnS plus 3O2 gives you 2ZnO plus 2SO2. If you have carbonate ore, that is calamine. Calamine is the ore of zinc and it is in the form of carbonates. In case of zinc carbonates, you have to use calcination. In zinc oxide, we had used roasting. Roasting was heating in presence of oxygen. In carbonate ore, we are heating in absence of oxygen, and it results in the formation of zinc oxide plus carbon dioxide. So both the ores we have got oxide. Once we get oxide of metal, it is to be reduced by suitable reducing agent. Zinc oxide can be reduced with the help of carbon, and on heating it will result in the formation of zinc metal, which will be impure. Impure zinc is called spelter, and it can be easily refined with the help of electrolytic refining. If you want to extract copper from cuprous sulphide or copper glans, first step will be roasting. In roasting, cuprous sulphide will change to cuprous oxide plus sulfur dioxide gas will be formed. To balance it, 2Cu2S plus 3O2 gives you 2Cu2O plus sulfur dioxide, 2 moles of sulfur dioxide is formed. Here we do not need external reducing agent. Rather, internally cuprous sulphide can act as reducing agent. It is also called auto reduction. We can also call it basimerization. Here the copper formed will be impure because it has spots or blisters due to sulfur dioxide. It is to be refined with the help of electrolytic refining. It is not necessary that in all the reduction we use carbon as reducing agent. Those metals which are moderately reactive or not so less reactive, in those cases aluminium is used as reducing agent. For example, if we want to extract manganese, we have to use aluminium as reducing agent. It will result in the formation of Al2O3 plus manganese will be formed. To balance it, we have to take 2 moles of Al2O3, it will be 4Al, here it will be 3MnO2 and 3Mn will be formed. There is thermite process. In thermite process, Fe2O3 reacts with aluminium on heating and result in the formation of molten iron and aluminium oxide is formed. Why do we get molten iron? Because this reaction is highly exothermic and molten iron can be used for repairing broken railway tracks. In the end, I'll advise all the students to go through this crash course very carefully. You can rewind it whenever you require and it will be very useful for your examination to prepare as well as revise your syllabus in minimum possible time. We wish you all the best in your examination.